write down a couple of, especially the examples that we were doing today. So here's the example of how do you set up a generic rate law. This is a generic rate law that just relates reactants and products together through their general format, which is not like a rate one, a 0, 1, or 2 order. It's not an integrated rate law. There's about 3 or 4 different ways we can indicate the rate laws with relationships to other things. So absolute rates can be indicated by rate, like the true rate value is equal to -1 over A, which little a is a coefficient, and with respect to the change of concentration of a reactant over the change in time. So this is just a format we will actually be talking about a little bit more today. But if you were doing this in relationship to a product, what would the relationship of A be to D? Well, you'd relate through coefficients because you're talking about like as A is consumed, D is made. Well, if this is a 1 and this is a 1, well, they're consumed and they're produced at the same rate. Yes, because they're 1 to 1. Got me? But if it were 2, it would be different. You would say, you know, A is consumed, let's say a 2 is there twice as fast as the D is produced. But the way that it's indicated here is we do a fractional coefficient, or we use the coefficient as a fraction. But if it's consumed, we put an addition sign, so D is a product, so it's being produced. So it'd be 1 over D is a coefficient, and then times the change in D's concentration over the change in time. So you can see that I'm doing something with respect to time. It's just a rate, though. It's change over time. Noise. Okay, so change over time is what we're indicating. Though there is truly one rate, truly for a reaction, if you're talking about it with respect to different reactants or products, the number changes. But it's still the same rate, it's just with respect to different reactants and products. It's still occurring at the same rate. So that's just one thing to note, that sometimes occasionally we'll express things this way. And so you'll see something related to this in a homework example and then also in what we're going to be talking about today. So just want to show you that before I left this slide. This was from the other day. So the coefficients help establish the with respect to that particular coefficient or that particular reactant. So 29 is that exact description. The lights down. Oh, so sorry. Okay, so if the rate for this, I don't have the question right in front of me, but for the rate for this particular example of chlorine plus fluorine yields chlorine trifluoride, there's our reaction. What you were given was that chlorine was consumed at 0.012 molar per second, and so that negative there is just representing the fact that it's consumed. Generally, we never ever write rates as negatives. We just say consumed or produced, but occasionally you will see that. So understand that negative is just meaning it's consumed. And so if you're trying to figure out the rate of consumption of the other reactant, which you can see the ratio is a 1 to 3 there, you implement a 1 and 3. So this is why I specifically want to go over this one, because I wanted to see what you guys could relate, but this is a good method of doing this. So you check your rate of chlorine, but that's related to fluorine in a 1 to 3 ratio. So in this case, you put your coefficient on the bottom. So -1, so the negative is there just because it's consumed. The 3 is on the bottom because of the fluorine. The X is our fluorine's change in concentration in time. So when you solve for X, you get 0.012 times 3. So it's consumed 3 times as fast, which in this case is 0.036 molar per second. Doesn't that make sense with each other if you're looking at the coefficients? So the setup is a little interesting because you're like, well, we're putting 3 in the bottom, not the 3 on top. But mathematically, that makes sense because we achieve a 3 times the rate of consumption because of 1 to 3 ratio. Yeah.
Why is it not -2?
It is negative as well. I think it maybe said consumed in the question. So if I say the word consumed, it takes care of the negative. But you could also have the negative there. I adjusted it because I wanted to make sure that generally we never put rates as negative value. But if you put the negative, it just means you're consuming. So, but that makes sense, right, mathematically. And then the last part was finding the production of the product. And so you can see, you can mathematically solve for this the ratios as well. It's a 1 to 2 ratio with respect to chlorine trifluoride. So according to chlorine, which was given to us, 1 to 2, because it's being produced, it is a positive value. That 2 adjusts to say I'm producing twice as fast, so 0.024 versus 0.12 of the chlorine trifluoride from the chlorine itself. It's just that how the structure looks is an interesting way to say it, but I think mathematically it just makes sense to multiply by its coefficient. Can I get a thumbs up if you're okay with 29? Even if you got like part A and B or two of those, you can get the last one. So 33, was that the next one you guys want me to do? Okay. So this is one that we spoke of from a graph, but the graph for your particular instance was said, tell me the average. So this is not at a specific time. Instantaneous rate is at one time you find the slope, and that's what Dinky and Sean did, right? I won't forget that charade. So that was at one particular point. But then who did the average? Did somebody do the average? No one did average. Okay. So average rate, I always take really close to the end and really close to the beginning because it's going to give us our average rate from start to end. And so I took my 25 seconds terminal time, 0 seconds initial time, and did y2 minus y1. So basically you guys are doing the slope of change in concentration over change in time, because rate is change in concentration over change in time. So if you do your relationship y2 minus y1 over x2 minus x1, so rise over run, plug in your values of your concentration at these two times, 25 seconds and 0 seconds. Again, just like we did temperature, temperature is always T final minus T initial. Everything is final minus initial. Everything in physics and chemistry, calculus, everything. So that's why I did T final of 25 minus T initial of 0. So you see the change in time. Let's see if I can move this over. There you go. You get 0.01 molar per second. And again, since we're talking about rate being, I think this is production of HBr, HBr, I changed them a negative to a positive. You just have to think about the fact that rates generally expressed as positive values. And then second, it said find the instantaneous rate. So your 25 seconds was your given time. At that given time, you draw a tangent line. There's my little sketch over here. And so your tangent line gives you an opportunity to choose a beginning and an end. And so you choose a y, or x1, y1, x2, y2. Same story. Do rise over run. So change in y over change in x. So that gives you approximately 0.00966 molar per second. But again, your tangent might be a slightly different angle than my tangent, so it would have been close. Or you can just, if you knew the equation, you could plug in your calculator and just do the tangent at that point, but we didn't have that much information. But I want you to see that you have graphical information for rates, data tables for rates, and then today we're doing time with rates. So it's a lot of, this is a heavy math unit, which makes some of us very happy, but it also makes us pull back on our background knowledge quite a bit. So that's the integrated, and then it said, what was the rate of consumption of bromine at time 50? I think is what the question read. So at time 50, just going to scroll down just a tad. We had at time 50, in particular, I drew a tangent line there, found my two values at the kind of the decent ends of your tangent line. So sometimes you draw in the middle of the graph, you just have to manipulate it so it's a little longer or shorter so that you can actually get a good data point. But rise over run, so y2 minus y1 over x2 minus x1 saw 0.0068 molar per second. And so this is rate of consumption of bromine. I can actually get the graph for you guys. But that's rate of consumption of bromine. And then according to the reaction right here, you can see the relationship between bromine and hydrobromic acid is a 1 to 2 or 2 to 1 ratio, whichever way you think about it. So if this is being consumed, what's the relative rate of production of that? Double, because of the 2 there, right? So it should be double the production of hydrogen bromide or hydrobromic acid, whatever it's said in this case. So that's what I did down here. I took my rate of consumption and I doubled it to show the rate of production. So just using your vocabulary, consumption and production is important there. And this is a question like this could be asked on a free response question, because you see how like they are very much A through D could be related to each other. They're like big chunks of questions. And so on our graph in particular for bromine, for bromine, it was something like, I don't know, something like this. So bromine was being consumed and hydrobromic acid was being produced. Well, how would this look different for the graph of hydrobromic acid? First of it would be going up, right? But what slope? More steep or less steep? more steep. It needs to be double the steepness, basically, because we're producing it twice as fast. You got me? So it should have been something kind of like this, but try to draw that so it looks steeper. It would have to be a decent graph for me to give you your credit. If it looked exactly the same steepness, I wouldn't give you your credit. If it looked like it was a little bit greater, I'd give you your credit there. For a quick sketch of how does hydrobromic acid rate of production form. So that should be steep. Okay, so that's what I think we're going to stop for now. Is that okay? The rest of those that weren't too bad is what K, units, and orders of reaction. But this is the stuff I knew we would struggle with a little bit with. All right, now actually, we're integrated rate law. All right, you need to stand up because you're on that sleepy bus. Get off the sleepy bus and stand up. Okay, so tell me, give me a thumbs up that you already know this. You already know that there's many things that can affect the rate of reaction. There's like 5 of them that we know. Okay, we know that in some cases we're really going to be focusing on concentration, which is what our primary conversation has been surrounded around, correct? Next week we'll talk about temperature's relationship a lot more, but right now we're just focusing on concentration. How does it influence the rate? And sometimes there's first, second, and zero order. We know that we can look at the impact of concentration changes on the rate changes, which is table logic, yes? We can decide from table logic, from the data, the rate of or the order of reaction. Now we're getting into one. This is something like what we did today: change in rate over change in time. We can figure out the rate that way, or relative rates. We can write rate laws like this. We're masters at, I think, mostly at this. Some of the complex ones were complex because they're abnormal. They have like fractional units or fractional orders. And then we can also figure out rate from a graph of concentration versus time. So right now we are like beast mode on rate. Like we can find rate in 6 or 7 different ways. But now we're going to add one more to the toolbox, and that'll probably be it for determining the rate. So in terms of math, if I want to be able to use, hold on, let me think how I can phrase this. If I want to make a relationship, I can't just make a relationship and go, well, these things are related. Related and correlated are 2 different things, and then correlated and directly related or indirectly related are also different things. Some of those have just qualitative reasonings, some are quantitative reasonings. So, what mathematical value can show as a correlation between variables? R squared, and we call that the correlation constant, right? You guys have taken math, but I know I'm going to be reviewing some math, and also you're like, new math? What's she talking about? Okay, R squared is our best friend for telling us, is something correlated very linearly, or is it not correlated? So a good R squared value would be what? So 0.99. What would be a bad, meaning not correlated variable? 0.01. Okay. Something like 0.7, 0.8. Those aren't even that good. Okay. 0.99 is like what we want. So if something is not, so if we put in our calculator 2 variables, an x and y, in our list 1, list 2, wherever you guys put in your stat plot, and you don't get a 0.99, what do you say about that relationship? It's not linear, or could they still be related? Yeah, they could still be related, but not in a linear fashion. So when I say linear, really I'm talking about linear regression. And linear regression always has one equation that's associated with it. What is it? Y equals mx plus b. So in chemistry, we strive to create some sort of mathematical relationship between 2 variables where we get a great linear regression line. We get a linear regression line that's so linear, the R squared value is 0.99. Now, this linear regression line can be a mixture of variables. So, like for example, Beer's law, right? Beer's law is basically a linear regression. A is our y-axis. A, B, which are those constants, right? That's the constants, which definitely could be related to slope. And X is C, meaning the concentration. And in Beer's law, what's the y-intercept? If I have 0 concentration, what should my absorbance be? 0. So we just don't write that because it's stupid, right? Beer's law is a linear regression line. We love it because it gives us great predictability power. So in kinetics, we can actually integrate things with, yeah.
In the absorbance side, we did y-intercepts equal like 0, 0 something?
Probably because of the contamination on the sides of the glass or something in the lab itself. It really should be very close to 0. It should be approaching 0. No little tail end on it. Okay, so we can actually integrate things with time. So as a reaction occurs, the concentration of something should go down, right? The concentration of a reactant should go down as time proceeds. Well, that relationship is different if it's first order, second order, or zero order, the mathematical relationship. So we're going to find a relationship where just simply concentration and time are related through the linear regression system here. Sometimes we have to modify concentration. It's not just concentration. It's not just molarity. It's the natural log of the molarity versus time. And then we can even modify more. We could do the log of the concentration versus time. We could do 1 over the log or 1 over the concentration. We can modify this mathematically as much as we want. But our job is to figure out, okay, I can do concentration versus time. I can do ln of concentration versus time. I can do 1 over the concentration versus time. And if I plot all of these in my calculator, and one of them gives me a linear regression line that's correlated at 0.99, that's the relationship. All this other crap doesn't matter, but you have to trial run them sometimes to see which is the relationship that works. And whichever the relationship is, that also tells you the order. And so this is what you did a little bit of your reading on. Do you remember seeing some of this, a little bit of this in your reading? You saw graphs like if I did a graph like this, this, and this, which of those looks most linear? Second one looks most linear. And all I've done is graph my data in accordance with these mathematical manipulations. So this one being the most linear, sorry, this is versus time. If that was most linear, this indicates to me it's a first order reaction. If the concentration versus time is the most linear of all my data sets, it indicates to me it's a zero order reaction. If the data fits best with 1 over the concentration, it's called second order. So what you do is you don't know the order at all for the reaction. You just got a bunch of data. You plug all your data in your calculator in these different ways. Since you don't know the relationship, you have to put all 3 sets of manipulated variables in there. And so whichever is the most correlated tells you the relationship of the reactant to the rate of reaction. Give me I kind of think I know what you're putting down. Who can repeat kind of in better terms what I just said? Go try it, Levi.
Whichever of those 3 methods looks the most linear will tell you whether it's first, second, zero order.
Right, so if you don't know which is first, if you don't know the order, but you have all this great data, what are you supposed to do with the data? Like, you can't do anything with the data except for manipulate it mathematically, because everything has a mathematical relationship. And whichever one fits best shows us that is the order of reaction. And you guys can collect data like this. You can collect concentration versus time, and that's what you guys will be doing on Monday. All right, let me work through some of the math here, because these relationships have really, really specific equations that go along with them, and I think the practice is going to actually be a little bit clearer for us. The only thing I really want you to tell me is, do you remember these log rules? Do you remember that if you have 2 things multiplied to each other, it's the same thing as saying log of A plus log of B, or ln? Ln and log are, not the same thing, but mathematically the same. If you have something where you have a fraction, like ln, natural log of m over n, that's basically the same thing as subtracting those 2 separately. What is this from, Math 2?
3.
Math 3? Who's in Math 3 right now? Nobody, great, okay, perfect. And then if you have something, and this is kind of what we did with our ugly algebra, if you have something where you have an exponent, like n, up there, that n, because it's really hard to manipulate something with an unknown variable, as an exponent, you pull the n down to the front as a coefficient with your natural log or with your log, and then you can then solve for that value. Thumbs up, you remember those. I remember those from, I don't know, calc or whenever I took algebra 2. Okay, so with our integrated rate laws, and this is like kind of the big idea for today. With our integrated rate laws, we're always integrating things with reference to time, because that's what integration means, is with reference to time. What we've already done now is we know that, this is on the other side, we've done concentration and rate relationships, which we look at a data table for, but now we're going to be looking at graphs and looking at time relationships. So our data tables will not have rate in them at all. Absolutely no rate. Our data tables will have concentration, and they'll have time, but they won't have rate. And they'll have that, for a number of different times. There won't be different trials They'll just be different times in that same trial. So in your lab, if you say, I'm going to run 5 trials, you'll be there all day, people. Run 1 or 2 experiments. Track your data over time, and you're done. You'll have unlimited amount of data, but you'll have every second of time accounted for. Does that make sense? 1 trial, all the data through 2 minutes or 3 minutes or whatever time you want to. But a lot of our reactions when we deal with integrated rate law, we deal with 1 reactant. We say that 1 reactant is either 0 order, 1st order, or 2nd order. We don't deal with like 2 reactants or 3 reactants a whole lot because it gets very messy. So that's what we will collect data on so we can derive our own rate laws. So let's talk about rate laws now. First rate law that we already know about is one like this. You know what that is. That's 1st order rate law. But if that's a differential rate law, we need to figure out how do we create an integrated rate law, which this is the integrated rate law. If you want to write that down, that is the 1st order integrated rate law. And that rate law is derived through calculus. But I'm going to just briefly show you that because I want you to have basic memorization is not always the key in science and math, right? Having a little bit of background understanding is very important. So even if you don't understand the calculus, I want you to at least see. I have the process already written out. You don't have to write the calculus down. But what you'll notice is that I've already told you, of those 3 relationships we just talked about, the only one that would be considered 1st order is if it's linear between ln of the concentration and time. What's this little k guy? Rate law constant, right? For 1st order, we already know the units it should be because we can manipulate and figure that out. But what we are actually doing now is tracking the concentration change over time, like literally doing that. So on the graph like this, doesn't this resemble y equals mx plus b? Yeah, basically. So this is y. Go ahead and maybe sketch a graph for yourself. ln of a is the y-axis. What's the x-axis? Time, right? That's mx plus b, right? So time, generally it's going to be in seconds. It could be in minutes. You just have to look at the data. And so what's the y-intercept? ln of a, right down here. And I'm going to be really specific. This is ln of a initial. And I'm putting it here. It could be anywhere. Sorry. It could be anywhere on the y-axis. It doesn't tell you it's at 0. I didn't mean to mislead you. It could be anywhere. It's whatever the ln of a initial is, the initial concentration. And so this k value is our slope, right? Is it a positive or negative slope? Negative. So if it's linear, it's straight. There's basically what our graph would look like. But what you would then do is, from your data, you plotted this, you have your y equals mx plus b, so you have your ln reg. If I was like, hey guys, find the rate law constant, you're like, well, hold on, let me go in there, plug in the trial, find k. No, you don't have to do that. How could you find the rate law constant from your graph? Find the slope, and not even find the slope, scroll on your calculator where it says a, right? Isn't a your slope on your calculator? That's your rate law constant. You don't have to calculate your own rate law constant if it's on your graph. The slope equals negative k. Well, rate law constants can't be negative, right? So just take the absolute value of that, and you'll have your rate law constant just from the graph, which is very nice. It's a nice change of pace. Okay, so what we need to do is now think about, if I have this information, great, I have the integrated rate law for the 1st order. How do I figure out the half-life of something? Well, what's the definition of half-life? Who remembers that from back in the day? Yeah.
The amount of time it takes for half of it to decay.
Okay, so if I was looking at my data or my graph here, the amount of time it takes for half of my initial reactant to decay, right? So let's say, and this is ln of a, this is not true values, but let's just work with this. If I had this much initially, where would my halfway point be of how much that concentration is at halfway point? How would I know that from here? I asked that question very weirdly. Where would my half-life time be on this graph? Go for it. Okay, so looking on your x values, which is your time, right? Halfway down the graph, because that should be that's the time it took for half of it to decay or to be consumed. So this is a linear, this is a natural log, but assume this is just concentration. So halfway down the graph, half of it's consumed. Look at your x, boom, that's your half-life. The time it takes for half of this to decay or half of it to react. Now, of course, this is an ln one, the concentration one, for another one will be much better to look at. But if you don't have the graphical data like this, maybe they give you information, you actually can plug it into an equation, which we're going to figure out right now. So let's look through the math part of this first. Before I get to half-life too in depth, I do want you to know, though, this is very important, every half-life you've ever done, ever, has been first-order half-life. Because all the half-lives we've done have been things that are related to radioactive decay. Radioactive decay is not dependent whatsoever on the concentration of a substance. If I said, okay, guys, half-life of carbon-14, or carbon-14, it's like 5,600 years. If I have like a kilogram of carbon-14 or a gram of carbon-14, does it matter how much I have? The half-life itself is still 5,600 years. It doesn't matter how much I have. It doesn't matter at all. But so what you're going to find is that half-life for first-order reactions has nothing to do with concentration. It's a time issue. So that's what we're going to derive right now. And so here's the initial part. So work with me. You don't have to write all this down, but work with me first on understanding. Rate that we know exists comes in many variations of how we write it. So we can write it like this: it's change in concentration over change in time for first order. We can also write it as just initial rate is equal to K constant times the concentration to the first power. We've seen both of these before. In the back of your calculus textbook, you have integrated laws or integration laws, right? I did not make these up. Okay, those would just be utilized to solve this process. So I'm just going to show you the basics first. I'm not spending very long here, but you should respect the math. It's there. Okay, so what you do initially is you take your rate and you rearrange to get your A values on the same side, and then you can integrate with respect to change in time, which is what this is. So we rearrange this. So I see my calculus people going, yep, okay. So then this is an integral. This little shape thing is an integral. And so this is initial concentration to the final concentration, but that's occurring over a set amount of time. Well, a set amount of time is here. And so as you utilize these your integral rules, you plug this information in right here. Or those tell you what you can achieve, what you can do. So you can see like K delta T, derived T, what's the D stand for? Derivative? Okay. That's going to be equal to KT, so that change comes away, KT. And then this is ln of x. So I've taken my AA, I've changed it to, ln of change in A over A. Sorry, this is a little messy here. But what was my rule for if I divided something? I could then not make it a subtraction problem, right? So I've integrated and I've applied my log rules or my ln rules, and I've taken my A final minus my A initial. However, that negative still existed. That's why it's still here. And so it's starting to get to be like a linear regression equation. It's getting there. I'm not there yet, but I've fully integrated. I'm done with calculus. Now I'm just doing algebra 2 or algebra whatever, and I'm taking my information, rearranging as needed. So I need to distribute this negative, and then I need to get the KT with one of the ln's on one side. So as I do that, I've distributed my negative. I've divided by negative on both sides here. So then ln final is equal to ln A initial equal to negative KT. Remember, we're supposed to have a negative there for a first order reaction. And then I've actually successfully made this resemble my linear regression equation. So I did some calculus to get there, but there is that relationship. You might have to know a little bit of background in college. But at this point in time, this looks exactly like we had. So I wanted to get you here first. So now let's apply the half-life rule. You guys said the time it takes for half of the concentration to disappear, right? So the time, instead of calling T, I'm going to call it T1/2 to represent the half-life. And that's all that right there is. We just talked about all that. What does that say? Oh, it says time. Okay. I was like, can't read my own writing here. Okay. So for half-life, T1/2 is achieved when the concentration initial gets to half of its original amount. Does that right there make sense? The time it takes to get to half of the original amount, so A initial over 2. I have to take this value and plug this in to the concentration final, which is A final is what I'm calling that. So if you are given this, you have to know how to derive your own half-life equation, or you can straight up memorize it. But if you memorize it, you got to keep tabs on that, because I'm better at deriving my own than memorizing. I think some of you guys are in that same boat. So what I've done here is this is the final concentration at the time of half-life. I put T1/2 in place of T just to represent I'm doing half-life. And so this being the concentration final, this is my initial concentration. How do I solve for T1/2? What would I have to do mathematically? Binky, tell me what I gotta do mathematically. But I don't have T, that's what I'm solving for. How do I solve for T though? Okay. What if I subtract ln's? What do I have to do with them? Alvin, go ahead and pick up from there. Okay, so after I bring my ln's together, I subtract them, I end up having to, let's see, I subtracted on that side. KT is over here by itself. I went ahead and fixed my, because my time needs to be a positive time, like I can't have negative time, so I just went ahead and fixed my negative sign, so I had a positive on my time side. And then when you rearrange your T1/2, your ln's together, this actually is subtracted because of the negative sign in the front. So I have taken my ln of A naught, which is my initial, minus ln of A2, which is now divided, because that's how you bring your ln's together here. You guys picking up what I'm putting down here? A little bit. This is K T1/2. This is my time I'm looking for. And so this is a copy dot flop right here. Yeah.
So if you're trying to solve for T, why don't you divide by K?
You can, but I would wait to do K at the very, very end. That's when you'll see me do it at the very end. So I just was trying to rearrange my ln information. So this 2 came to the top. A naught and A naught cancel each other out because they're both A naughts, they're both the same. And so that gave me ln of 2 is equal to KT. Well, then that's when I divided by my K on both sides. So then I got ln of 2 over K is equal to T1/2. Sorry, equal to T1/2. ln of 2 over K is equal to T1/2. If that's all you memorize, I understand, but I'm giving you some respect to the math. However, anybody knows what ln of 2 is? Like, I don't know what ln of 2 is, but if I memorize it, I will know it. So what you do need to memorize that ln of 2 is 0.693. Because if I ever give you mental math problems, you're like, I don't know what the ln of 2 is. I can derive it, I got all the math, but I don't know how to get the ln of 2. So that's 0.693. And I believe this is given to you in your reference table. Does anybody have the reference table handy? The green one I gave you? Look on the back of that, Kurt. And so, tell me it's on the bottom right-hand side, ln. Okay, so if they give you 0.693 over K, you have to know what that stands for, right? You're just going to go, well, it stands for half-life. But then you have to know, is it half-life of 0 order, 1st order, or 2nd order? So it's not so much like, oh, it's on my reference table, I don't need to memorize it. You also need to know what it's used for. So one thing to note is, do you guys see concentration in here at all? No concentration. So does concentration play a role in the half-life of a 1st order reaction? No. Okay, and so that's where I was trying to demonstrate this earlier, but as concentration initial goes to concentration half, meaning the half-life has been achieved, that time there would also be then your time of half-life. Yeah. It does if it's a 0 or a 1st order reaction. 0 or a 2nd order reaction. It's only for 1st order that we actually have some idea of, which is our radioactive half-life we've always dealt with for all of our life. But there's half-lives of other things that are not radioactive. Okay. That are not 1st order. Okay, so let's apply that in a second. I'm going to show you guys this as well for the other 2 orders. I may not walk through all the math right now, but I at least need you to know for a 2nd order reaction, this is your integrated rate law. Write down your integrated rate law. I'll hopefully take about 5 more minutes here. So the integrated rate law means that ln of A, or ln of concentration of time, is not correlated. It's not linear. They might be correlated, but the R squared constant might be like 0.6 or something. ln has nothing to do with 2nd order now. 2nd order reactions are integrated with 1 over concentration final and 1 over concentration initial. You can see this is a K value, right? But it's not negative, it's positive. Yeah. Is that what you're going to say? So it's the way the math works out, which is on the next page. I'll briefly show you that. But it does work out so the math is not, it fixes itself. It negates itself. So what does this graph look like? What's my y-axis? This is what I think you definitely need is initial information in the graph. Say the y-axis again. 1 over the concentration, right? This is y, this is mx plus b. Okay? What is the x-axis? Time. And then how does this graph look? Positive or negative slope? This one's a positive slope. Second order is a positive slope. First order is a negative slope. So how do you get the k value? How do you get the rate law constant? Find the slope. If you have it in your calculator already, which you guys will need your stat plots today, we'll do that in a second. You just need to look at your stat plot value for your, once you've done your linear regression, take your slope, that is your rate law constant. Okay, so in this case, half-life definition still applies, but what was the half-life equation for first order? No, what was the half-life equation for first order? 0.6 times 3 over k. Sorry, I heard like one person say that. Okay, so this one's different. This one is different. I'm going to show you that now. Is everybody ready? So there's all the integration underneath here. I'm just scrolling quickly through this. But you'll notice that the squared applies here. The integration rules are different. That's why this equation is different, because we're talking about squared, which is different. So that's why when you plug in your values, you do 1 over x, which is what the integration rules state to do. So that negative applies, which causes it to flip, and so that's why k stays positive. But after you get done with integrating, you get down to your rate law, integrated rate law, which we just wrote down. We're good here. We just wrote down our graph, so we're good there. But here's how, at the same, for the same instance, you get T1/2 is the time it takes for the initial to get to half the concentration. So that's what I would then be doing here. Down here just a little bit. Sorry, I wrote a lot here. So same thing applies. T final is equal to half the initial concentration, which is what that means. I throw that value in. I rearrange my math, which is not hard at all, but I get down to here. Write that down. That is your half-life equation for second order reactions. Notice you do have concentration in there, right? 1 over k times initial concentration. Yeah? Concentration's in there. Okay, so that means that the concentration of that particular reactant does influence the time of half-life. So why does it influence the time, or how does that look? Well, that means every single half-life is different for a second order reaction. That's why we don't talk about that in radioactive decay, because that gets really complicated, right? So each successive each successive step of that reaction is twice as long because the concentration gets smaller, smaller, smaller of initial. Yeah. So it's not very often we see this. That's why generally we don't talk about it in like general chemistry or even in biology when we do half-life, because it's not so often we see a second order half-life. But that's your equation. And your K would come from what again? Slope. Okay. Zero order, last one guys. Zero order. You know that this is true for zero order. That's our rate with that K value being really the only thing that's controlling the rate because the concentrations are useless for a zero order reaction. And so when you integrate it, it's a nice equation with no natural logs, no fractions. It's just how the concentration relates to the time. And that's because there's not a whole lot to do with the math behind it. It's just how does concentration affect the time, but the concentration is not important to the rate, which is kind of a catch-22 there. But in terms of the graph, what does this graph look like? Say again? So why is it down? Negative slope, okay, but it's only a negative linear line when you have concentration and time plotted. If I had ln in concentration and time plotted, it would be like a slope or a exponential decay graph. If I had 1 over the concentration versus time plotted, it would be like some weird flunky log graph. It wouldn't work. It wouldn't be linear. So it's only linear for zero order with this relationship plotted. So many times, and this is a fact I think I told you the other day, that many times for these zero order reactions, we do require a catalyst to bring the reactants together, because the reactant concentrations don't play a role into the rate itself, but we do need it to occur, and so occasionally we need a catalyst to do that. And those can be biological catalyst or catalyst on a metal surface. An example of that would be a catalytic converter. And what does a catalytic converter do in your car? So it's catalytic, which means what? What's catalytic sound like? A catalyst, there's a catalyst in your car converting something before it puts out your exhaust. What do you think it's converting? Harmful pollutants. Okay, so you got like nitrogen monoxide possibly coming out of your tailpipe. Let's see, nitrogen monoxide, carbon monoxide, maybe a sulfur dioxide. Those are all pretty bad things to inhale. They do not smell good. They smell horrible. So what we do is we convert them to nice things like carbon dioxide. Yes, I know it's a greenhouse gas, but it's better than carbon monoxide, and converts it to things that are less likely to pollute. So a catalytic converter is actually a zero order reaction in your car. Fun fact. All right, another fun fact, and then we're gonna do problems. Oh, I gotta tell you the half-life. Sorry, half-life. This is integration. If you're not a calculus person, you're not probably finding this quite as fun as I am. Okay, half-life, half-life. Here you are. Here's your half-life for a zero order reaction. Here's how you calculate if you have your initial. This is A naught, by the way. If you have your initial concentration of your reactant, it's concentration over 2K. All right, so recite those for me. Don't look at your notes. What was first order half-life equation? Over K, so 0.693 over K. No concentration. Second order. 1 over K times the concentration initial. Okay, and this is the only one with 2 in it, right? Well, kind of. Okay, which is, this is a zero order. Concentration over 2K. So memorize them if you wish, or learn how to derive them. I can walk through that math again soon. The math is a little overbearing, so I'm trying not to let that depress you. I'll show you about, I took a medical pharmacokinetics class this summer. I was going to show you guys something with that, but I'll go over that real life example in a little bit, because I was going to show you my paper from grad school. It's not important right now. Okay, so here's your data table. This is in your notes. Find this for me. It's on page. Have your calculator out, and we're going to start integrating. Not integrating, stat plotting. Stat plotting. You guys find this in your packet? I think that's titled integrated or integration notes. Yeah. It's on page 11 in your notes. Page 11. All right, here's your calculator. You got your calculator out. You need to make sure you know how to plug this in the stat plot. I'm not trying to be ignorant that some people haven't done this in a while. I mean, you guys have different calculators than I do, so I have to work with your calculator. So, you with me? Okay, pull up your stat plot. If we were integrating with time is always on what axis? X-axis. Go ahead and plug all your times in X-axis. If you don't have a calculator that does stat plot, sit next to somebody so you can see it. If you forgot your calculator at home, I have a loaner. And make, they're all dead. These are all dead. I don't know. Thanks. All right, so FYI, we always have to do all three relationships because we don't know what the order is, right? You have to do time versus concentration. So in your stat plot, you guys have L1, L2, is that how you do it? Okay, mine's called something different, so L1, L2. You're going to do time in L1, which is your x-axis, we'll call your x. L2, straight up do concentration. Well, what relationship is this trying to prove? Zero order. Then you'll do time versus, so this is going to be one whole list. Let's just start with that. We'll do natural oxide. Let's just start with this one, because then I'll show you guys how you can just play with your concentrations and plug your natural log in the whole thing. When you plug in these 1, 2, 3, 4, 5 data sets, do linear regression. So this is in stat plot. Then do lin reg. And tell me your R squared value. I got 0.6. Can I get a second on that?
0.607.
0.6-ish something. Okay. Yeah, make sure your diagnosis is on. Give me a thumbs up if you made it that far. I'm trying not to leave anybody in the dust. The dust is nasty. It's dead. Look on with somebody for a second. Alright, give me a thumbs up if you made it to 0.6 as R squared.
Yes,
Just please sit next to somebody so I know that you've got this. You got it in your calculator? Because I can't, my calculator is different than yours. I'm like an idiot on these calculators. I got mine down, but I don't know how to use yours. Alright, so on your graph that's on your notes, please go ahead and put down concentration. You guys have like a little graph, right? On your notes. Put concentration versus time, and then put R squared underneath that is 0.607. How does that graph look to you? How does this graph look?
exponential curve.
Okay, is it, so zero order, does zero order have a, does this relationship have a negative or positive relationship? Guys, with me, if you're talking to the person next to you, just hold off for 1 second. Thank you. This concentration versus time should have a negative relationship. It's not straight, because it's not linear. It has a little curve like that to it. So sketch what that looks like, because then you should say, nope, not zero order, not linear. You're supporting your decision with data. All right, so then now go back to your lin or your L2 list and ln all those. Natural log all those concentrations, because you already got your concentrations in there, right? Just natural log them all. I think you can natural log the whole column at the same time. I think. Natural log all of the concentration values. Anybody? What'd you get, Kurt?
It's the second one looks like the first one, and then the third one is
Give me, I need an R squared value for the natural log versus time. Let me just make sure. I got a couple people tell me different things. And I'm looking for my notes.
0.85.
What'd you get, Arishi?
So the way I did it was I went to L3 and like
You just, okay. So an alternate method, either one, go to each of your concentrations and just put ln in front of them, and that will adjust your L2 list, or make an L3 list that natural logs your L2 list, which might be nicer because then you can go back and check your work too. But either way you do it, what should be your R squared value? 0.8 something?
Yeah.
0.85. Is that linear? Not really. What does this graph look like? Okay, so like the first one. So natural log is the negative slope one, but it's not a straight line, has a little bit of a curve to it. Okay, so this is us disproving not zero order, not first order. So then it has to be second order if we've done something wrong. Oh. But now I'll do the same thing, but 1 over the concentration. So either go back to your L2, plug 1 over concentration in all those, which is a little bit of a turd because we just ln them all. Or go into L4, make an L4 list of the 1 over of L2. Give me a second. Let's get everybody caught up for us real fast. Because you do need your natural logs, because then we're going to need the slopes, so don't delete your data. We're going to need that slope. Anybody R squared for this one?
0.9999.
Can I get a second on that? 0.999? Okay, what does this graph look like? Straight line, up or down? It is the only one that's a positive slope. Just remember, second order is the only one with positive slope. What is that slope, by the way? What's the slope? Please tell me the A value.
9.198.
9.198 units per second order K value. Think about that for a second. I'm not going to tell you, I was going to wait on you first. Sean, Binky, what's up?
I'm trying to figure out how to find the unit.
Is it diagnostics on? Okay. All right, so you guys tell me the units for this. The units, of course, are not given to you in your calculator. You have to think about a second order reaction. You have to think about a second order reaction. Think about the units what K would be. So this is K is equal to, and this was the slope 9.189 is what Kirk told me. Your guys' should be really close. Say it one more time, Courtney.
K over molarity squared.
Well, no, that you're telling me rate. I mean, I just want to know the units of K. Molarity seconds. Yep, that's it. This is K value. K value, and we should hopefully. Oops, sorry. We should hopefully be okay thinking. Okay, so I got my K for my slope. Units of K for a second order reaction. Don't forget, second order reaction is rate is equal to K A squared. Rate. So rate has to still be molarity seconds per second. K is going to adjust the molarity squared to negate one of them. So one molarity has to be in the K. And the seconds don't appear in the equation, they have to be appearing in the K. So that should be our K value. Okay. Give me a thumbs up if I went just the right speed. Make sure we have some. Okay, I got it. Let me do another one like this. So first question was, is the rate law 0 first or second? We figured out it was second by graphing them all, finding the most linear relationship. That's proving it's second order because the relationship is between 1 over concentration and time. What is the K for the rate law constant? Well, we looked at the what? Slope. And then what is the half-life according to the initial concentration? So think about second order, half-life, and what's the half-life equation for second order? Initial concentration over 2K?
That's 0.
That's 0.
Oh, that is 0 order. Sorry, we're doing second order. So 1, ready? What's our initial concentration? Oh, you guys should probably write it down. It's on your sheet. It's on your sheet. What's your initial concentration? 0.1. So then 1 over 9.1, oops, sorry. 198 per molar seconds times, what was that, 0.1? Okay, so guys, we're talking about time, right? What should be the only unit left? Seconds, right? And if that's not right, we've done something wrong. But in this case, that we're good, because what's going to happen? Molarities cancel. Seconds go to the top, right? Because it's on the denominator of the denominator. So take that divided by our combined denominator. What's your value?
1.09.
I don't have that value on my paper, so I'm guessing you're right. Put that down. I didn't write it down. Tell me one more time. And I need a second on that.
No.
I just want the final value. What's the final value?
1 point.
So
1.09.
1.09. Thank you. Okay. Because it needs to be 1 over 0.9.
Oh, it's the 1.
Yeah, 1 over that. I was like, it can't be 0.9. Okay, so the half-life of this reaction is 1 second. That's what we just figured out. The half-life of this particular reaction for the first part is 1 second, basically. Yeah.
And then as soon as the rate law constant.
We figured that out by doing the rate law constant is K. And we did it by looking at the slope of that particular relationship. All right, again, second one. Look on your sheet. Do you see the second example? Do it all by yourself. Talk to your people at your table. It's on your paper.
You're like 4 triple at that.
I don't have any AAAs. Please complete the second example in a timely fashion. I still have more to do with you because there's some manipulations of this I don't have. I have lots and lots of golf. please raise your hand if you need help putting things in your calculator. If you're like, I'm still not quite sure if I need to start my calculator. Just want to make sure. Now, you don't get to stop once you think you got the linear one. You have to disprove the rest of them. All right, does anybody have values for zero order? 0.97. 97 what? 97? 3? I got 1.5, whatever. Okay. Does anybody have first order? Okay, so that's looking promising. And second order? 0.97. So like I said, though it could be very linear, don't stop and go, got it. Let's double check them all. The most linear relationship does not exist between concentration of time and 1 over concentration of time. The most linear relationship exists as a first order relationship, ln of concentration versus time. What do each of these graphs look like? Which one's the positive slope one? Second order, right? That's kind of like a slight curve to it. Zero order has a slight curve to it. First order, is it positive or negatively sloped? Negatively sloped. What is the slope? 0.049 units. Because remember, this is K, right? Per. Say again, loud and proud. Just seconds. How is K just seconds? Well, because it is in terms of time, but what's the rate law for first order reaction? Rate's equal to K times concentration to the first power, right? So if this concentration gives me a molarity, I got molarity, right, for my rate? So then, if this gives me a molarity, this has to give me time to create molarity per time. So that's good. This is 1 over a second, hence why we did slope to be K, which is, it is negative, but is K negative? K is a rate law constant. It's telling us about the speed of a reaction. You can have a negative speed. In chemistry, you can. Okay? Not deceleration here. All right, so, what was the next part? Oh, no, we got it. So K, rate law constant. What is the half-life equation for a first order reaction? 0.693 over K. No concentration, right? If I had to find the half-life of this, I could do it by plugging in 0.693 over the K value itself, and I could find the half-life. Or I could actually plot the data in a concentration versus time. I could look at the concentration versus time graph, and I could find the half-life. Definitely could. You also could look up here. You can approximate the half-life, maybe, for a first order from a graph. So about 15 seconds. So can anybody, go ahead and calculate that for me real fast. I don't have my calculator. What is it? 19.2. Yeah, sorry, 19.2 seconds. Yeah, I tried to guesstimate from the graph, but from our data, but our data is kind of too far apart for me to guesstimate that to give me the time there. So, but it does correlate there. You got me? Because it goes from 1.4 to about 0.7, so that's between the 13 and 20 mark, which is 19.2, obviously closer to the 20 part because this 0.8 or 0.68 is very close to 0.7. So you can graphically or data analyze. Okay, analyze. Okay, one more for us. I'm going to choose these. This is in your question set. It's on the page 12 in your packet. So some of these have a little extra variable involved with them, and so I just want to make sure you can stat plot it up. You can look at your data, find your data on your calculator, and move. But these have a little bit of a different idea to them. So you guys tell me how you would approach. How would you approach number 1? Hold on. Let me read for a second. All right. So Jacob, what were you gonna say?
Okay, so I would do like at 0 seconds. There's 1 gram and like 1 molar, I guess.
Let's do 1 more since we're talking molarity. Okay. Why are you doing this? Why are you telling me you're making it up?
Like molarity listed, so once the unit number is
Okay.
listed,
That's always how I start.
And then after 80 seconds, it's 25% is gone, so it'd be 80 after 10.75 moles.
Okay, so we're saying 80 seconds is our time. We're saying this is a first order reaction. First order reactions have a integrated rate law of what? What's our integrated rate law for first order? What's our Y? Natural log of concentration. Is this final or initial? Final. And I'm using A. I could put cyclobutane in there, but I'm not. Sorry. Equals negative KT plus ln concentration initial. Okay, so it told us it was first order, so we got the integrated rate law. So then he said, I don't know all my variables. I'm looking for, what am I looking for? Oh, looking for the rate law constant K. You don't have any data, right? Now you can't graph it and find the slope. So you must plug values in. So if you're plugging values in, you have to look for those values. And if you don't have them, make them up. It's okay to make these up. And I would start with 1 because it's an easy number. So he said, let's say A initial is 1 molar. So then A final is what? Y.75.
Because 25%
Decomposed, right? So a quarter of it decomposed, leaving us with 0.75 to remain as final. Then you can solve for K. So sometimes they give you enough data to plug into your equation. Sometimes they give you data to plug into a calculator. Go ahead and solve for K. Write out your work. You guys need some sample problems to look at before you move on. I have about 15 minutes before I do two more. So I like to just rearrange variables versus plug in values at first because it makes my life easier. So if you're rearranging this to solve for K, you need to combine your ln's, ln of A final minus, because you're pulling your ln over here, ln of A naught equals negative KT, but you're solving for T, correct? No, solving for K. So what are you going to divide by? Negative T. So if I rearrange like this, are you guys okay if I rearrange like that? You pull your, so net minus ln of A to the other side, so minus ln of A, and then divided by negative T to keep K by itself. So this is what K is equal to. So you can plug that right in your calculator with your variables of interest in there, or you can combine your ln's and divide them because it's being subtracted. Maybe that helps you with your calculations. But once you start plugging in, what's the ln of 1? Isn't that 0? It is 0, right? Okay. So that's gone. It's very nice. I'm just verifying it's 0 because I can't always remember that sometimes. Yeah.
In a problem like this, can we just pick any initial concentration?
As long as you decline it by 25% of it, yeah. I would say decline it, it's easy. So as you guys are maybe observing, you're calculating some. I'm doing these examples so that you guys understand. It does take some math here. Ln of these two values, you think the molarity stays. The That's okay. Calculation level. You think the molarity stays because you're like, well, the molarity's there. But mathematically, that is actually ln of 0.75 molar over 1 molar, right? Isn't that mathematically the same? What happens to my molarity units? They cancel. There is no molarity left. This is where your units will get screwed up. The seconds do remain, right? They stay with us. So that is per second. And that is K. Sorry, that's our final here. It's 3.6 times 10 to the negative third per second. Noticing that this negative was negated by the ln of a 0.75. So the negatives negate each other to give us a positive K value overall. Yeah. I will help you derive them as we go, but in case you ever need to do it yourself, you just have to match the units, right? So if this is what is this, first order? Right, this is first order, according to my problem. Rate is always molarity per second. K varies, and this is just concentration, right? So this concentration being molarity, and it's first order, so it's molarity to the first. I need to get something here that makes molarity stay and seconds come to be. Well, I can't put molarity per second because that would then be molarity squared on this side. Not the same, right? So I can't have anything in the numerator. It has to be 1, or just the number that K represents, per second. And so this would be modified if it were second order or 0 order. So if it's 0 order, K takes care of everything, right? K takes care of the units. K is the final rate. So if it was first order, it's this. If it's 0th order, it's molarity per second, because that takes care of K and rate. They're the same thing. And if it's second order, what is it, Alvin? Second order. Per molarity second, right? You need that. You need that 1. Don't cancel both your units. You see what I'm saying? You picking out what I'm putting down? Alvin? Why is it just molarity second? Because if you put, because if it were molarity, if this was a second order, this would be molarity squared. And so that means if I left it as is, molarity squared would stay, and that's not true. So I need to have 1 molarity in the bottom and cancel one of them out. You can memorize your K's or just derive them yourself, so they always should make sense when they match.
So first order is just first second.
Yep. So that's our first answer. How would you then find the half-life? At, say again? Divided by the K value. Okay, I'm skipping over that for now. That's a plug and chug method. Okay. The one I want to do is number 3, number 3, and then number, another one. I gotta look for it. Okay, this one, yeah. So the rate law constant for a second order reaction is 48 liters per mole minute. What does that actually mean? You guys know what this means. Per what? Is it molarity per minute? Per molarity minute, right? Because this is liter per mole, which is opposite. So this is saying 48 per molar minute. That's what we just said second order was, molarity from the bottom. Okay, at a given temperature, how long will it take? So what's our question? Time, we're looking for T. How long will it take to decompose 90% of a 0.2 molar solution? So we have first of all, we have a second order reaction. What's the second order integrated rate law? Say again? 1 over concentration final equals positive or negative K? Positive KT 1 over A initial. And I could put the nitrosyl bromine, I'm not. We could plug that in there. I'm just putting A for now. What am I solving for? T. Okay, manipulate this to solve for T. Subtract 1 over A, I hear you. Initial. Subtract 1 over A initial and divide by K. So this becomes 1 over A final minus 1 over A initial all over K to give me T. Math heavy, guys, right? Math heavy. What's my what's my initial? 0.02, just 10. That it? Okay. What is my A? How do I figure my A final if 90% is decomposed? Say again? So 90% decomposed, I have 10% remaining, right? 10% remaining is 0.1. So just making sure we can achieve that by ourselves. So 0.020 molar times the 10% remaining. 10% is a decimal is 0.1. So that is 0.0020 molar. So here's my initial. After 90% is decomposed, I just have 10% remaining. So here's my final. So then plug. And do I have K? I do. Oh yeah, sorry. I do have K. I didn't write it down. 48. K is 48 molar minutes. Go ahead and plug. Make sure you're calculating correctly. I'll throw some numbers up here too to help you check. If you're sitting there and you're just watching, then I hope that you're good on the calculator. Sometimes they get a little tricky in the calculator. What's the opposite of ln if you had to calculate opposite of ln? Say again? E. E, caret. Whatever E, I don't know what E's called. It's called E, right? Doesn't have a name? E. Give me a thumbs up if you got 9.4. 9.4. Ooh, do you guys know how to use the solver feature of your calculator? I taught some of you guys last year. There is a solver in your calculator. You can put X in there and it'll solve for X. That's another day though. I don't have time right now. I got 8 minutes. Okay, so you guys look through. I'm gonna do this first. Give you guys a second there. It is whenever. Look at the problem set, which is right under 1 through 6. 1 through 6 are the examples that I was gonna do in class. But if you feel like you're okay and you'd like to attempt some of these, then go ahead and look at 1 through 9. Back, go. So 1 through 9 is underneath. Do you see those? Looking at your packet in front of your face. Look at 1 through 9 and tell me if you want me to do one of those. But if not, you guys have time right now to start that. If you want to work with somebody, work with somebody. But if you want me to do one of them, you're going to tell me this is your problem set. So it moves to the next page. I'm good to do one of these with you to get you started on the problem set. If not, you need to start. Do not sit there and waste your time. Not 1 through 6. You have 1 through 9, and then I'll show you guys where your graphing worksheet is. Look at this nice summary that you have in your packet as well. Rate law, half-life. You have this in your packet, I think. Is this in your packet? There's a little graph. Look, I guess a little chart. Okay, I know you have your packet on hand right now. Do you see on page 6? I gave you page 6. That's got the rate law, units of K, integrated rate law, a sample graph, and the half-life expression. So highlight that baby section because that's going to be your go-to. But you should have most of those memorized. Like you should know how they work together. Don't just depend on that. But that's a good chart there for reference. But homework. I will show you where it is on the website, but you need to right now work on at least 1 or 2 of those integrated rate laws from 1 through 9 from your problem set. My computer is frozen. My computer is frozen.
Attention staff, just to let you know, we will be honoring senior privileges today. Thank you.
Wow, it doesn't apply to me.
Because Deborah wanted to let you know.
She was everything. Am I gonna reach across all the way? I'm not that
Girl.
Don't even try.
Oh my god, ready to make this turkey or something.
Are we about to?
I did on mine.
Let's pick up. Throw it out.
She won't do that because I'm gonna forget everything over the food.
Like this? I don't know.
Oh yeah, I heard you.
Are you hearing you now?
Yes. Yes. Oh yeah. My computer's frozen. I'm trying to stop this video. Did you appreciate the calculus?
Yeah, I know that.
I was like, okay, everybody's kind of like dying right now, so just stop. But I like that. It's kind of nice to understand where things come from. So it's not just memorizing. At least it's like, it's not as fun. I always really like when I went from calculus to chemistry, or whatever it is, to college, and biology to chemistry. It's just like things are in other classes, like it matches, it actually makes sense.
I know I've come to like a lot of these factors.
If you're doing anything with time, which for us is only 2 weeks, it's the only really time issue we deal with. Like, we look at with equilibrium, but this is the basic. This is the analysis side.
That's pretty cool.